Dear students, in today's lecture, we will discuss derivation of a very important inequality in statistics known as Chebyshev's inequality. First of all, we talk about the statement of Chebyshev's inequality, that is given for a random variable x, maybe a discrete random variable, maybe a continuous random variable. In today's lecture, we will derive Chebyshev's inequality for a continuous random variable. So if x is a random variable, it is the statement is given for any kind of random variable, maybe continuous, maybe discrete, taking only non-negative values. That means normally a random variable may be positive, may be negative, may be any integer value if discrete and any real value if continuous. But here in any case, whether it is continuous or discrete, it can possess only non-negative values, and it possesses a finite mean. That means mean of random variable x is finite, which is mu, and its variance is sigma square. Then for any particular instant t greater than 0, we have a certain inequality that probability of this particular content, that is probability of mod x minus that mean mu greater than equals to that time t that contain t, and that probability is always less than equals to sigma square upon t square. That means that value may be equals to sigma square upon t square or strictly less than sigma square upon t square. That means any probability of this kind can never exceed the value of sigma square upon t square. Let's talk about its proof. We start with that left hand side of inequality, Chebyshev's inequality, p mod x minus mu greater than equals to t, and we are deriving it for continuous random variable x. That's why it is defined in terms of integration. If mod x minus mu greater than equals to t, so probability is mod x minus mu greater than equals to t up to infinite fx dx, where fx is certainly probability density function of that continuous random variable x. Now as mod x minus mu greater than equals to t, so if we divide it by t and square both the side, what will happen? Mod x as t is positive, so by dividing it by t, in nature of inequality will not change, and it becomes mod x minus mu upon t and then whole square, so x minus mu whole square upon t square greater than equals to 1 in right hand side of that inequality. So using that mod x minus mu greater than equals to t, we obtained one very important inequality, that is x minus mu whole square upon t square greater than equals to 1. And because of that, what happened to that initial step? Left hand side is obviously same, and it is equals to that content, and we are now multiplying that integrand fx by x minus mu whole square upon t square. As you can see, x minus mu whole square upon t square is multiplied with fx, but as it is greater than equals to 1, that's why that probability which was equals to that right hand side is now less than equals to that particular content. Why it is coming as less than equals to? Because the probability in any case can't be greater than 1, and we multiply it that particular integrand fx by a quantity which is certainly greater than equals to 1. So if that quantity is greater than equals to 1, then that probability which was equals to that content must be less than equals to that right hand side now, because of that only it can counterbalance itself to maintain it inside one. Now we start the proceedings with that inequality mod x minus mu greater than equals to t again, and that is obviously made by these two components. How? Because that mod x minus mu may be written as x minus mu or mu minus x. If it is written as x minus mu, then it becomes x minus mu greater than equals to t, means x greater than equals to t plus mu. And if it is written as mu minus x, then it becomes as mu minus x greater than equals to t, ultimately x less than equals to mu minus t. So if that particular inequality is written as these two partitions, so what will happen to equation 1? Equation 1 means equation or last step of previous slide. Left hand side of that equation 1 is obviously same. In right hand side, that is taken as sum of these two. So right hand side is sum of two terms now, as x less than equals to mu minus t means minus infinite to mu minus t, and x greater than equals to t plus mu means t plus mu or mu plus t to plus infinite, as you can see. So it is about certain changes in equation 1 because of these two components of that inequality. Now what we are doing? We are adding one term in between these two terms in right hand side of that equation of that inequality. Which term is added? 1 upon t square, same content, 1 upon t square x minus mu whole square fx dx with limit mu minus t to mu plus t. And as that right hand side is obviously greater than left hand side as looking there, and in that greater term we are adding one more term, so it is obviously greater. So that inequality is still maintained by adding that positive term. And why we added that term, limit mu minus t to mu plus t? Just to fill that gap between mu minus t to mu plus t. And by adding those three terms, now minus infinite to mu minus t to mu plus t to infinite, those three terms are added in right hand side with same content. Obviously the limit becomes minus infinite to last one plus infinite. So it is equals to is not in place of that less than equals to is for sum of three terms of right hand side only. That left hand side and less than equals to it is still maintained. Okay, so sum of three terms of right hand side is 1 upon t square x minus mu whole square fx dx inside the integration minus infinite to infinite, as I mentioned, and it is nothing but sigma square upon t square. Why? Because 1 upon t square is outside, and that integral minus infinite to infinite x minus mu whole square fx dx is definition of variance of continuous random variable x. That's why it is written as sigma square. So left hand side is still there with that less than equals to is there, and in place of right hand side now we can express sigma square upon t square. So finally p mod x minus mu greater than equals to t less than equals to sigma square upon t square. That is about completion of all important Chebyshev's inequality in statistics, and that inequality can be proved for discrete distribution in similar manner. In place of integrals, summation convention sign of sigma can be used. In next lecture we will discuss several important problems in connection of Chebyshev's inequality.